the previous lecture we were discussing about streamlines, streak lines and path lines, and we have defined this formally, but when it comes to the determination of these lines in a functional form, there is always some confusion in the mind of the student when the student confronts to a real practical problem. To get a feel of that, we will work out an example. So, because of the time constraints and all, in the regular lectures I will be discussing only about limited number of problems and more concepts, but I will talk about certain essential problems which build up the concepts. So, the question is that let there be so first question is find the equation of streamline passing through x0 y0 z0 at t equal to t0, and these values themselves be 0, but may be 0, but this is just symbolically we are considering something. Then locus, or maybe we can put it in a little bit different way, equation of a colored die or equation of a colored line that is visible as a consequence of dye injection at dye injection or continues up to say t equal to 2 t0, and the third is locus of a fluid particle that is injected at x0 y0 z0 So, we will try to work out an outline of the solution to the problem rather than really working out the full algebra. So, equation of streamline, the part 1. So, dx by u is equal to dy by v, it is a 2-dimensional flow field, because the w is not there, dz by w is not relevant. So, you have dx by u is x t plus t0 is equal to dy by v is v0. Now, the most important thing is that the streamline equation has to be obtained at t equal to t0. So, this t has to be substituted t0, okay. Then the remaining is very trivial algebra, like dx by x is equal to dy by 2 t0 v0. So, y is equal to 2 t0 v0 ln x plus some constant. How do you evaluate this constant? you evaluate this constant by noting that this streamline passes through x0 y0, that will, so you put x equal to x0 and y equal to y0, that will give you the value of this constant, straightforward enough. So let me erase this because I do not want to erase the problem definition, so I will use this part of the board to work out the solution. Second is equation of a colored line that is visible as a consequence of dye injection. So then that is what is the equation of a streak line. So in the streak line concept, what you are doing? You are actually finding out locus of a particle, but not a single particle, locus of different particles which have passed through a common point. So when you write that velocity of the particle, this is the relationship between the velocity of the particle and the rate of change of position, right. Because at a given point the velocity of a fluid particle is same as the velocity of flow at that point, that is the Eulerian and Lagrangian descriptions merge, this is u, and normally x particle is same as x. So see, this is a conceptual gap. In the books straight away the problem solution writes u equal to dx dt. The confusion that comes to our mind is that it is a description of a flow field eventually. So how u should be equal to dx dt? The reason is that you are actually referring to u of the particle, but because u of the flow is same as u of the particle at that point, so u equal to dx dt. So you have x by, and similarly v is equal to dy dt. So u is equal to x by t plus t0 is dx dt. So dx by x is equal to dt by t plus t0. Question is, what will be the limits of integration? Okay. So the dye is injected where? At x equal to x0, right. So the dye is injected at x equal to x0. At what time it is injected? Over a period of time which is variable. So it is a time ti, where the ti is from t0 to the final time 2 t0. This is where the students make mistake, and it should be clearly pointed out that this is not t0, but a variable time ti which you do not know, but it is over a range from t0 to 2 t0, okay. And the final location is, say, this is x and this is t. So you have ln of x by x0 is equal to ln of t plus t0 by ti plus t0, right. Similarly, which one? Upper limit will be 2 t naught, right. So this will be 2 t naught, right. Then dy by u v is equal to dy dt, let us write it here, utilize this part of the board. So v0 is equal to dy dt. So if you integrate it, dy is v0 dt. So integrate, again the limits are ti to 2 t0 and y is equal to y0 to y. So this will give you y minus y0 is equal to v0 into 2 T0 minus Ti. So, what you can simply do is you eliminate this Ti from these two equations, and that will give you the locus, right. We will keep this part of the board now and find the locus of a fluid particle that is injected at x0, y0, z0 at t equal to t0. This is the path line. So, why the students are confused is because your starting step is still the same, u equal to dx dt. So, the third part, so x by t plus t0 integrated, so dx by x what are the limits of integration now? Now at x equal to x0 the particle is injected at which time? T0. Now this T0 is fixed, what is variable now is this T, right. So you have ln of x by x0 and similarly you have v is equal to dy dt. So, dy is equal to v0 dt, integral dy is equal to integral v0 dt. So, your time starts with t0 to t, this is x, y0 to y. So, y minus y0 is equal to v0 into t minus t0. So, now what you eliminate? You will eliminate t from these two equations. So, to summarize, here you are eliminating the final time, whereas in the streak line you are eliminating the initial time. That is the basic difference that is coming into the picture, although they appear to be elusively very similar calculation, path line and streamline. So, streak line. So, you can clearly see that streamline, streak line and path line, although we have not worked out the final answer, but at least from observation you can gather that these are not same in terms of equation. But there is a particular situation when these lines converge, and we will discuss that in a moment. That special case is the case of a steady flow. Let us say there is a particle which is moving in a steady flow field. So, particle is now at P1, after some time it is P2, at P2, after some time it is at P3, after some time it is at P4, like this. So, the path line straight away is this one. Now, because the velocities are not changing with time at a given location, whenever the particle comes here, it will be guided in the same direction. So, when there is a particle which is here at whatever time, that will be guided in the same way as the particle was guided maybe a few minutes before. So, this line will be such a line where tangent to this line will always represent the velocity of the flow. So, this line also becomes the streamline. Not only that, whatever particle is injected through this point at whatever instant of time will be constrained to move along this line only, because the flow field does not change with time, and therefore, this also becomes the streak line. So, for steady flow, streamline, streak line and path line, they converge, they become identical. Okay. And one artifact of this is that whatever you visualize in a steady flow experiment as a streak line, you can also call it as a streamline. And this is the propagation of a misconcept that, you know, when a student is told that in an experiment a streamline is visualized, it is not fundamentally a streamline, but it is actually a streak line. Because it is a steady flow, the streak line is eventually same as the streamline. So, this conceptual gap needs to be rectified in the class. Okay. The final concept that we will discuss in today's lecture is a very important concept, which is the acceleration of flow. So, acceleration is a natural consequence of time rate of change of velocity. That is why after studying velocity we are studying acceleration. So, in terms of continuity in discussion, there is no ambiguity about it, that why should we study acceleration after velocity. The big question is that what is the big deal of, you know, studying acceleration. We can just similarly say that acceleration is, if somebody writes that acceleration is dv dt from, you know, the basic school level mechanics, what is wrong about this? So, the first thing is that this we can write if the velocity is described from a Lagrangian perspective, but in a flow field you are describing the velocity from an Eulerian perspective. So, what is that equivalent equation which will include parameters from the Eulerian perspective and not from the Lagrangian perspective? That is why you require a separate derivation. So, imagine that, you know, there is a particle which at this point has velocity v, which is a function of the position and time t. This is the Eulerian description. So, this includes x comma y comma z, say in a Cartesian description. Then after some time the particle has come here, it has a, let us say, velocity say v plus dv or v plus delta v, which is a function of x plus delta y, delta x, y plus delta y, z plus delta z and t plus delta t. So, when the particle has come to a new position, two things have happened. One is the position has changed, another is time has also changed. These two things have changed together. So, acceleration along x. How do you define acceleration? Fundamentally in this way, if you are focusing your attention on the particle. So, limit as delta t tends to 0 u at x. So, this in a functional form we do not write v plus delta v, we just write v at the nu x, nu y, nu z and nu t, right. So, u at x plus delta x, y plus delta y, z plus delta z, t plus delta t minus u at x, y, z, t divided by delta t. Okay. So, new x component of velocity of the particle minus old x component of velocity of the particle divided by delta t, right. The basic definition of acceleration, time rate of change of velocity of a particle. So, now u at say t plus delta t, x plus delta x, y plus delta y, z plus delta z is nothing but u at t comma x comma y. I am just writing t first because I will write the time derivative first, that is why I am writing t first. So, u at this plus higher order terms in the Taylor series. This HOT very commonly in this course when we write it means higher order terms, that means terms of the order of delta t square, delta x square, delta y square, delta z square, cube, fourth order up to infinity. This is a Taylor series for multiple variables. So, you can write acceleration along x, the difference between these two divided by delta t. So, and for the higher order term, if you divide by delta t and take the limit as delta t tends to 0, all the higher order terms will vanish. So, now the conceptual understanding comes. So far this is just Taylor series expansion. So, this is straight away 1. What is this? Limit as delta t tends to 0 delta x by delta t is the x component of velocity of the particle, right. This is the y component of the velocity of the particle and this is the z component of velocity of the particle. Now that you make delta t tends to 0, the previous position of the particle and the new position of the particle they converge, and therefore the Lagrangian description and the Eulerian description at that point they merge. This is very important. This is the subtle concept that you must discuss about, that as you make delta t tends to 0, the Lagrangian and Eulerian descriptions merge, and then this becomes the velocity of flow along x, this becomes the this is Vp, right, not sorry. this is UVW. So, this is WP. So, this is Vp is equal to V and Wp is equal to W. So, acceleration along x becomes so clearly there are two different types of expressions in this. This talks about steadiness or unsteadiness. So, this is called as unsteady or temporal component. Temporal means time dependent, and this is called as convective component. So, physically this is the change of velocity, acceleration due to change of velocity at a given location just due to change in time, and this is physically due to the migration of the particle with fluid flow from one location to another where the particle finds a different flow field. So, the net acceleration is a combination of these two, and you cannot really say that what is the net effect. For example, let us say you are taking a flight from say Kolkata to Mumbai. So, when you started from Kolkata, say it was raining, and when you landed in Mumbai, then you also see it is raining, but it could be a culmination of so many things. For example, when you started from Kolkata, it was raining at Kolkata, but it was dry at Mumbai. But when you have landed up in Mumbai, it is raining in Mumbai, but it might have dried in Kolkata or it might still have rain in Kolkata. So, the net effect is a combination of spatial and temporal effect, the position dependent and time dependent. Yes.
Sir, it is having description of both time variation and space variation.
Yes, it is having, just allow me to repeat, it is having description of both time variation and space variation. Then
so whether it can be considered as a Eulerian approach or convergent?
no, this is a Eulerian approach, because in the Eulerian approach the velocity is a function of position and time. So, both time dependence and position dependence comes into the picture here. So, one interesting thing is that even though you have velocity as a function of time, but acceleration can be 0, right. For example, let us say as an example, just hypothetical example, this is 1 meter per second square and this is minus 1 meter per second square. Then although velocity is changing with time, still you can have 0 acceleration, right. So, this is some non-intuitive thing that comes out of the Eulerian description. So, you have the combined spatio-temporal effect together to emphasize on that. This is not called as d dt, which is given for Lagrangian frame, but it is called, it is given a notation of capital D dt, which is the total derivative. So, it contains both spatial and temporal effect in an Eulerian description. This is called as total derivative. So, acceleration along x is du dt in a vector calculus notation. This is what it is. So, you can write the velocity vector as ui plus vj plus wk, and the nabla operator operates on u, it is a dot product of these two. So, we are always interested to write a vector form because vector form is coordinate system independent and it can be used for other coordinate systems as well. So, similarly acceleration along y is dv dt. And acceleration along z so now if you take multiply this with I cap, multiply this with j cap and this with k cap, the unit vectors, and just add, you will get the acceleration vector is dv dt okay. So, to sum it up, we have discussed in this lecture about the flow visualization through streamline, streak line, path line, and we also have developed a conceptual foundation for expressing the acceleration in terms of the Eulerian variables. So, with this we stop here today. In the next lecture we will be discussing about deformation of fluids, which is very unique and very different from what you normally get as deformation of solids. Thank you very much for your kind attention. See you in the next lecture.